250 square by 4, y that is 25 given in the data, only the I that is of BD cube by 12, 100 into 250 cube by 12, and if we simplify this one, we achieve the answer as 2.88 megapascal, that is the shear stress variation at distance of 25 mm above the neutral axis. So if we are draw the variation, so please see on this tabletop, we know the distribution diagram. We know the distribution diagram is like this. This is neutral axis, and we found out this value is as 3 Newton per mm square, and this value we achieved from this part number 3, that is of 2.88. This is 0, this is 0. So we can find out the value of shear stress at any section. Whatever the section we are interested, we can find out the answer as per the basic fundamental equation for rectangular section. I wish you have understood this problem very clearly. Let us proceed for the next problem. Refer the data. Before going to further data, here there is an alternate method is also given to us to find out the shear stress at distance y is equal to 25 mm above the neutral axis. Means in the previous case, in the third case, we have used the very fundamental equation, that is f over f divided by this 2 pi, this one. We have used this equation, f by 2 pi bracket d square by 4 minus y square. This is the one of the approach. But if you do not know this fundamental equation, or if we have forgot this equation, even though we can solve this problem by using the basic fundamental equation, and that equation, that alternate approach is there with us, is this one, that is tau is equal to f a y bar by I b. This is my basic equation. So if you know this basic equation, even though we can solve this third option very well. How? It is understood right now. Y is equal to 25 mm given in the data, f that is 50,000 Newton, a is the area of beam above the 25 mm. Now the given rectangular section, which is the size of 100 by 250, so the distance d by 2 is 250 by 2, that is of 125 mm. Now 125 minus 25, that is the remaining area. So if you just refer this tabletop, then this available depth is 125 minus 25, that is 100. This is also given 100. So area available to me is 100 cross 100. So area available to me is 100 cross 100. That is same thing which is visualized on this PPT. Y bar is the distance of the CG of the area A from the neutral axis. Now for this figure on this tabletop, this is the CG to this distance. It is nothing but 100 by 2 plus 25, and that is 75 mm. So y bar, that is distance of the CG of the area from the neutral axis, that is 75 mm. I is the moment of inertia of the total section about neutral axis, that is 1 by 12 BD cube 100 into 250 cube, while B is the actual width of the section at a distance 25 mm from the neutral axis. B is the actual width at the level EF. At this level, it is nothing but 100. B is there because the rectangular section. So this 100 is remain constant throughout the depth. So by putting all these values on this PPT, if you are referring and solve this equation, then F is 50,000, A is 100 cross 100, Y bar is 75, I is the BD cube by 12, B is 100. We achieve the same answer as 2.88 megapascal Newton per mm square. So you can solve this problem either using the direct formula or by using the basic fundamental equation F A Y bar by I B. Proceed for the next problem. A timber beam of rectangular section is simply supported at the ends and carries a point load at the center of the beam. The maximum bending stress is 12 megapascal, 12 Newton per mm square, and maximum shearing stress is 1 Newton per mm square. Find the ratio of the span to the depth. It is understood this way. A timber beam of rectangular section which is simply supported with the central point load. Here, indirect value of shear force, indirect value of bending moment is given to us, not direct, because simply supported beam with the point load is given to us. We do not know the value of shear force, but it is given to us that maximum bending stress permitted in this is 12 Newton per mm square, that is sigma max is 12, while tau max permitted is 1 megapascal. It means precisely that if the bending stress comes beyond 12, my beam will fail, or if shear stress beyond one value, my beam will fail. So, if we proceed further, then let B is the width of beam, let D is the depth of beam, L is the span of the section, W is the point load at the center of the beam. The maximum shear force is W by 2 and maximum bending moment is WL by 4. Yeah, this is very much important. How these things will achieve? How this W by 2 and WL by 4 will be there? That comes the basic fundamentals of SF and BM. Let us see over here on this tabletop. Simply supported beam with central point load W. L by 2 is the distance. Now, what will be the reaction? Reactions are of W by 2. A question may arise, how? Obviously, if we are standing on our two legs at the center, the half of the weight goes on the one leg, half of the weight goes on the other leg. Similarly, this W is at the center, half of the load comes on this side, half of the load comes on this side. If you do not know once again this one, you can solve by using this equilibrium equation. Sigma V is equal to 0, RA plus RB is equal to W, and if you solve sigma MA is equal to 0, then this RB minus RB cross L plus W into L by 2 is equal to 0, and we achieve RB is equal to W by 2. Similarly, we can achieve RA is equal to W by 2. Now, if we plot the shear force diagram for the same one, then this is W by 2, no load, horizontal straight line, sudden change, shear force value, plus value, minus value, W by 2 with this sign convention. So you can visualize very clearly for a section the maximum shear force acting. W by 2. Now, next. This is the baseline. The value of bending moment is 0 at the two supports. W by 2 into L by 2, it is W L by 4. So this ordinate is W L by 4. And if with this answer is positive with this sign convention, so we achieve maximum bending moment is WL by 4. So we achieve maximum bending moment, we achieve maximum shear force. Now come to the point PPT. So average shear stress tau average is nothing but the shear force by shear area. Shear area is cross sectional area, and cross sectional area is nothing but B cross D. So shear force, that is W by 2, maximum shear force that we have already found out from the shear force distribution diagram, shear force diagram, that is W by 2 by BD, and we achieve W by 2 BD, that is the average shear stress. Now maximum shear stress is given by an equation. Tau maximum is 1.5 tau average. This equation is valid for rectangular section, and also in the data which has been given to us, the given section is of rectangular. So tau maximum value is given to us as 1 value. 1 is equal to 1.5 into tau average is equal to W by 2 BD, as the tau maximum, the value 1, it is given in the data. So if we are simplifying this 1.5 is 3 by 2, we achieve W by BD is equal to 4 by 3. We achieve a relationship between the point load and the cross sectional area as 4 by 3, but it is not our question. Our question is to find out the ratio of the B and D. Now in the data they have used the word bending stress value limited to 12 megapascal. When they have used the word bending stress, in that case we have to use the basic fundamental equation of bending, that is M over I is equal to F over Y, that is M over I is equal to sigma over Y. M is the bending moment, maximum bending moment acting at a section. I is the moment of inertia. F or sigma is the bending stress. Y is the distance from neutral axis. So maximum bending stress, sigma maximum, is equal to M over I into Y max. Interesting point observation. What will be the Y max? What is the value of M? What is the value of Y? Now if you are referring to this tabletop, then for a given beam maximum bending moment is WL by 4. So M is known to us. What is D by 2? What is the Y max? Let us refer the figure over here. Given section is of rectangular section. This is B, this is D, and this is our bending stress distribution diagram. This is my sigma maximum, this is tension, and this is compression. Maximum bending stress occurs at the top and the bottom fibers, and this is my Y. This is my Y. This sigma C max is equal to sigma T max. Given section is of symmetrical section. So Y max is equal to D by 2. So if we are putting all these things value on the PPT, visualize, then sigma max value given to us is of 12, M WL by 4, y max, that is d by 2, I BD cube by 12. VHU, by simplifying this, 12 is equal to 1.5 W into L divided by BD square. Now we have 12 is equal to 1.5 WL by BD square. If we are simplifying once again, 1.5 into W by BD into L by D. Now W by BD that we have achieved from the previous case, that is as W by BD as 4 by 3. So if we are replacing this value over here, 12 is equal to 1.5 W by BD, I will put the value as 4 by 3 into L by D, and we simplify all these things, we achieve L by D is equal to 12 by 2 is equal to 6. Means length or span of the section is 6 times the depth of section. This thing must be permitted only to satisfy the conditions of maximum bending stress and maximum shear stress. So we achieve the ratio of span to the depth is 6 to permit maximum bending stress 12 megapascal and maximum shear stress is of 1 megapascal. Once again, I wish you have understood these fundamental problems. So you just visualize in this particular problem, the three different thing is collaborated. The first important thing, shear force and bending moment. Second, very much important thing, that is about the bending stress equation. And third one, that is shear stress. So if you are going thoroughly, you can visualize that from the reaction, then SFBM, then bending stress, and then shear stress, all the four things are collaborated in single problem. So the fundamental must known to each and every student about all these things. Let us we go further with the next problem. Ready for the data. A simple